Okay. So as I said, percent composition, not to be confused with percent yield. So what is that? It's referring to, it is referring to the percentage by mass of a certain element. Sorry, that's not worded quite correctly. The word certain element appears twice. There we go. Percentage by mass of a certain element in a compound. And so it's a straight percentage, really. Any percentage is always the part that you're interested in over the total times 100. And this part of it especially is not difficult. It's just the mass of that particular element in total, whatever that element is contributing to the total mass of the compound, and then we multiply by 100. And I'll show you an example in one moment. So this is different than percent yield, which is talking about, if we do it like we did with the chalk, we did a chemical reaction, how much stuff did we get out of the chalk? This is a totally different concept, only related in the sense that they're both percentages. So for instance, suppose we wanted to know the percent composition of hydrogen in water. In other words, out of water's mass, what percent of that mass is hydrogen? So we would just add up the molar mass of H2O, which is one of those ones you've done many times. Maybe sometimes people even start to remember. It's about 18. Now the mass of hydrogen, there's 2 hydrogens, right? So I would take hydrogen's mass times 2. So out of the total mass of 18, 2.02 is coming from 100. So again, it's just a straight percent. We have 2 grams coming from hydrogen, 18.02 grams total mass. So water is 11% hydrogen by mass-ish. And the other 89-ish would be oxygen. Questions about that? So, we can, of course, do this for any element, for any compound. We'll look at a couple more examples in a minute, but just a couple of definitions and things like that to get this out of the way. I think that I've defined this for you at some point in the past, but just as a reminder, we can talk about empirical formulas versus molecular formulas. And as I said, pretty sure we've talked about this maybe at a couple of points, but the difference is that the empirical formula is the lowest ratio, whereas the molecular formula is the actual formula of something. Ionic compounds are always represented as empirical formulas, but covalent compounds composed of nonmetals only are represented as molecular formulas. So, for instance, C6H12O6, that's glucose. Whoops. Among other things could have that formula, but one thing that has that formula is glucose. You can kind of reduce that if you divide them all by 6, similar to reducing a fraction. You could reduce that to CH2O. And so there would be many compounds with that same empirical formula. So, CH2O, it could be C6H12O6, like you see there. It could be C100H200O100, or whatever other else would be in that same ratio. So there are many compounds possibly that would have that same empirical formula. a poem. And this poem is going to make more sense in a little bit when we go through some of these problems. But this way you'll have this here in your notes. What we're going to do eventually is we're actually going to find empirical formulas from percent compositions. And so the little poem to help you remember the steps is percent to mass, mass to mole, divide by smallest, make them whole. And we will learn what that means when we actually see some problems. But that's all the notes. And from there, we're actually going back to the beginning of this packet. I'm not sure what page it is, but it's the very first page. So this is page 169, and again, the top part just reviews some of the things I've just been mentioning. But just to show you just at least one more example of how you would do a percent composition. Question 1, way down there in the bottom, says verify that in C4H10 the percent composition of carbon is approximately 82%. So it's just saying, it's sort of telling you the answer in the question just for practice purposes is what it's doing. So the first thing we would do is we would add up the mass of this just like normal. So it'd be 12.01 times 4, which, oh, I'm sorry, keep doing that. 12.01 times 4, which is 48.04. And then for the hydrogen, we got 1.01 times 10, which is 110.10. So just normal adding up of molar masses. And then, so it's asking us for the percent composition of carbon. So we would just take this mass that we got specifically from the carbon, and we should get right about 82.6% there. And we divide that out. Yeah, so 82.6%, that's a 0. Questions about that? Take a second and just see if we can do the sodium and sulfur in Na2S. Pause the video if you're watching at home. So, you know, there's a couple different ways that we could do this. You don't actually have to, since there's only two things, you don't have to actually fully calculate both percentages. You could, for example, find the sulfur first and then subtract from 100% since they have to sum to 100%. That would be one way to do it. Or you could find both percentages, one and the other. Either way, we should be getting these. Questions about that? So I think, you know, hopefully we got the rough idea there. I'm not worried about 1C right at this moment, but if we go to the next page and we have that little table, I think I might want to actually project that. Give me a sec. I'm going to project that. Okay, so when we're looking at these thingies here, I wonder if I can ink on this. Yeah. We could just count, for example. What you're seeing is a variety of compounds. It's their structural formulas. These are kind of complicated organic molecules, basically really complicated Lewis structures, if you remember drawing those. And so we can count here, and we can see that that is C3H6. And this one is given to us already. That's C6H6. We can count these and see that it's C4H4. And then we can count this last one and see that it's C6H6. So what I'd like you to do is take a second and try to let's fill out at least these 4 boxes of this data table right here. So see if you can find, so we want to know the percent composition of hydrogen and of carbon in both of these. Now, just like we saw in the last one, if you can just find one of them, you could subtract from 100. So take a second, let's find, pick one, maybe you want to do the hydrogen. You know, find the percent of hydrogen, then you could just subtract from 100. Find the percent of hydrogen, this one, you could subtract from 100. So take a second and just try to find that much out right there. Okay, so looking at this, you know, for example, we figure out C3H6. We could add all that up, 3 carbons, 6 hydrogens, put it there, and then the mass from hydrogen would be hydrogen's mass times 6. And so it turns out that's 14.4. Since there's only 2 things, we could subtract from 100. And we're going to get 85.6. It is the same as that one up above, which we'll talk about in a moment. If we do this one, you end up getting 7.8, and you get about 92.2. So looking at that and going down to some of these questions that are down here, it says verify that the percent composition of, so it's right. You can calculate it if you want. So fill in the blanks. We've filled in the blanks of at least a couple. It says, can you determine a compound structural formula if you're given the molecular formula? Can you? If you just see this, could you automatically figure out the structural formula? No, that's an organic chemistry concept down the road of your chemistry career. But here we see 2 examples of things that have the same molecular formula but different structures and have they're just different things. What is true about the percent composition of 2 different compounds that have the same ratio of carbon to hydrogen? Yes, notice that they're the same. Notice that these have the same empirical formula. The empirical formula for both of these would be CH2. Both of them have twice as many hydrogens as carbons. And so because those ratios are the same, because those proportions are the same, like in the case of this one compared to this one, what would be different about the calculation is that both of these numbers would be double in this one compared to this one. And that would end up being the same percentage. If you double both these numbers, you're going to get the same percent. Point being, things with the same empirical formulas have the same percent compositions. So that's the take-home message of this. So it says, like, it is possible to complete the following table using only information in Table 1 without the aid of a calculator or a periodic table. Try it. Hint, consider question 6. So C8H8, what's the ratio of carbon to hydrogen there? 1 to 1. So we just need to go back and find some where they're 1 to 1, which are these 2. So without even doing the calculation, because we've already calculated, like, for example, both of these are 7.8 and 92.2, we would know automatically that that's what this is. So I know that's hard to see, but... And then when they're 1 to 2, like in the other one, that's the, 14.8 and 14.4 and 85.6. Questions about that? Okay, so this thing goes, basically what this is designed to, like, just by reading it, you could in theory learn how to do these problems. So it does have a nice little kind of walkthrough of how to do these problems. But we're going to go ahead and go to number 11 here. And I think I'm going to go back to the notepad. This is number 11 on, what page is this? 172. Number 11 on 172. Hopefully I'm recording the right things here. Okay. So it says, Find the empirical formula for a compound that contains 82.4% nitrogen and 17.6% hydrogen. Okay, so here is where we're going to use that poem that I mentioned earlier. It went percent to mass, mass to mole, divide by smallest, make them whole. Let's all say that. Repeat after me. Percent to mass. You at home, you say it too. Mass to mole. Divide by smallest. Make them whole. Let's do this one more time. Percent to mass. Mass to mole. Divide by smallest. Make them whole. Okay. First one is. One more time, everyone now. The first one is. The second one is. Third one is. Fourth one is. Okay, so this is what we're going to do. Percent to mass literally means change the percentage sign to a gram sign. Percent to mass. So here's the logic. Here's what I'm doing. I am assuming I have 100 grams of this stuff, and the only reason I'm doing that is because that makes this percentage conversion really easy. If I had 100 grams of that stuff, 82.4 grams of it would be nitrogen, and 17.6 grams of it would be hydrogen. So percent to mass, mass to mole means just turn these both to moles of the things that we're talking about. So this is nitrogen, right? So I'm just going to do a normal mole conversion for nitrogen. Now the part that is a little bit tricky, and some of us, I am going to use just nitrogen straight up, just normal mass from the periodic table, not N2. And the reason for that is because this is not, remember, the diatomicness only applies to literally the element nitrogen, like what comprises almost 80% of the air in this room. These are nitrogen atoms I'm talking about that are in a compound. So in this type of situation, where we're not dealing with a chemical reaction, we're not dealing with the element nitrogen, we should just use the normal mass, not the diatomic mass. Same thing with the hydrogen. I'm not going to use 2.02. I don't have a chemical reaction here. I'm just going to do the normal mass from the periodic table, which we're going to call it 1.01. Yeah, and so I'll get to that in a second here. So the reason you want to do this is it's this whole thing we're always talking about in stoichiometry. We have masses, which you can measure, but moles are numbers of things. Formulas involve numbers of things. So I'm going from a mass to a number of things, which is what I need in a formula. Now I know that there's a ratio here between the nitrogen and the hydrogen, which is 5.89 to 17.4. The problem is we need whole numbers in the formula. So when we divide by smallest, what that's going to do is it's going to normalize the ratio or turn the ratio into a whole number ratio, which is what we want. So percent to mass, mass to mole, divide by smallest. What that means is we're going to divide them by the smallest number of moles, which is 5.89 in this case. And the reason you do that, like I said, is we are trying to get these things to a whole number ratio. So when you do 17.4 divided by 5.89, we get 2.954. Uh-oh. I might run out of juice here. Okay, make them whole. 23 minutes, supposedly. All right. Make them whole means if you are very close to a whole number, just round it up. When I say very close, I mean like a tenth or less, probably. So if you're very close to a whole number, you just round it to a whole number. And this is close enough where we can just round this to 3. So percent to mass, we change the percentage to masses, mass to moles, do the mole conversion, divide by smallest, that's this part. Make them whole is just, I'm going to go ahead and round 2.95 to 3. And what that means is that the empirical formula is that 1 nitrogen, 3 hydrogens, it's NH3. Questions about that?
What would happen if you weren't
Good question. Is that your question too, Greg? Okay. Let's say we got to here and it was something like 1 and 1.501 or something like that. This is definitely too far to round. So the make them whole step would be multiply them both by some number that would turn them into whole numbers. Or at least very close to whole numbers. What would that be in this case? 2. I'm going to multiply them both by 2. Instead of rounding, I'm going to multiply them both by 2. And so to make them whole step, it would be 2 to 3. So if these were numbers, then it would be N2H3 or something like that. But not here. Go ahead.
Okay, so I was looking at it, and couldn't you, when I first wanted to say that, I can actually as well as then find them. And we draw the character of 3 out.
I see what you're saying, and possibly in some cases, but not. That's just not always going to work because, especially in more complicated things, it's not necessarily predictable. But it is possible, but I certainly wouldn't rely upon that because you never know. But I see what you're saying, and yeah, in this case, that would have kind of worked out. Other questions about that? So if we go down a little bit, it says the empirical, and this is a race against time till my battery runs out for the people who are watching this. Number 12 says the empirical formula for a certain compound is NO. This is the empirical, it tells us. And the molar mass of the compound is 60 grams per mole. It says, what is the molar mass of the empirical formula? Okay, well, so it's just asking normally, just add up the mass of that. So it's 14.01 plus 16, basically pretty much 30. So what this question is getting at is we can use this information to figure out what the actual molecular formula is. So this is the empirical formula. And so the real compound could be exactly that. It could be N2O2. It could be N4O4. It could be N100O100. Did I say 100? It could be some multiple of that. But check this out. Here's what we know. We know that the molar mass is 60, and we know that the empirical formula weighs 30. So if I were to divide those two things, I get 2, which means the real formula must be twice as big as that. And that's what it's saying here. It's saying B is what I just did right there. And so C is just saying, hey, can you figure out the fact that this is the empirical formula? The molecular formula must be doubly as big because it weighs 60. So the molecular formula would be N2O2. Okay, so let's look at another example of that sort of thing, which is 13. It says, what is the empirical formula of a compound whose percent composition is those? Okay, so percent to mass. Literally just change. So for my carbon, it's 85.7. This is 13A that I'm talking about. And for hydrogen, it's 14.3. So percent to mass means literally change the percentages to masses. Mass to mole, do a normal mole conversion using our masses from the periodic table. And again, the idea here is I'm assuming a 100-gram sample. That's 7.14. I'm assuming a 100-gram sample. You could assume you could assume a 5-gram sample and take those percentages and get the grams in a 5-gram sample. It would just be more work than you need to do. And in these kind of problems, okay, 40.16. Okay. So percent to mass, mass to mole, divide by smallest. So this is going to be 1. This is going to be very close to 2. So yeah, it's like 1, or yeah, very close to 2. So it's like 1.98. That is close enough that we can go ahead and round it to 2. And so therefore the empirical formula is CH2. One carbon for every 2 hydrogens. Oh, I can't make this go away. Now, if we had really been on the ball, we might have noticed that these were those same percentages from the table that we were looking at earlier, where the ratio was, where the empirical formula was CH2. But that's how we would have to figure it out if we didn't have that table and that extra information there. It still works. Yeah, I mean, it ends up working out to the same thing. They're close enough, I guess. Okay, so that's C. Now remember, that means that's the lowest possible ratio. The real formula could be any multiple of that. It could be CH2, it could be C2H4, it could be C3H6, it could be C100H200. So what I need to know if I want to find the actual molecular formula as in B is how many times bigger is the real thing. So we learned that the real thing has a mass of 56. And the logic here is I'm going to add up the mass of this, 12.01, call it. 2 hydrogens, 2.02, so that's 14.04. So this thing weighs 14.04, the real thing weighs 56, so we're going to divide them, right? Because what that's going to tell me is how many times bigger is the real thing. Now, when we're doing this step, you should definitely be getting very, very close to a whole number. If you're not getting something like spot on a whole number when you do this, you have made a mistake. So yeah, this is very close to 4, which means the real thing is going to be 4 times bigger than this. So what would it be? C4H8. And you could always, check, if you wanted to check your answer, like, does that actually add up to that? Which it's going to. But if you make a mistake somewhere along the way, that won't work, like it won't add up right like that. Questions about that? I'd like you to try, take a look at number 4 on 173. So I'm going to work this for our friends at home on a frozen screen. So in this case, because the 2.50 is too far away to round, remember we want to be very careful about rounding. We don't want to round more than a tenth. Instead of doing 1 and 3, for example, the make them whole step is going to involve multiplying them both by 2. So we get 2 and 5, and we get N2O5. So that's the general idea. Questions 6 and 7, just a couple of hints on those. First of all, for both of them, they mentioned AMU as a molar mass, 448 AMU. Don't be thrown off by that. That's the same as grams per mole. It's the same number. It's just a different weird unit. And if there are 3 things, you do it the same way. It doesn't change anything. 64.3 grams of carbon on number 6, for instance. 7.14 grams of hydrogen. And then 28.6 grams of oxygen. And we can just change all 3 to moles, divide all 3 by the smallest, and so on. And then for number 7, similarly, it gives us 3 different things there. The thing that throws people off on 7 sometimes is it asks for the molecular formula. I would still recommend you go ahead and find the empirical formula first. There is kind of a sneaky way we can go right to the molecular formula. If you figure that out, you can try it that way. But generally speaking, we need to go to the empirical formula first and then find the molecular basically the same way you did in number 6. Oh, oops.